Okay, in the last section, we talk about so what is software performance engineering? Talk about the process of software performance engineering and performance measurement. So in this section, we talk about the most important part of software performance engineering is performance testing. Okay. First, why we need performance testing, right? So large-scale software systems are usually used by many users. For example, Stack Overflow are used by millions of users. WhatsApp used by hundreds of millions of users, right? So this is the context of performance testing, and here we see not some other examples, right? So here the same system used by many users as well. For example, the AT&T Global Network Operations Center, right? So here we have many users operating the system at the same time, right? Other examples, SAP, right? So many users are using the system, and also the number of users are growing continuously. Here we look at this example. We just look at example from 2006 to 2012. We check Facebook, Twitter, LinkedIn, WordPress, and other websites. We see the users are growing continuously, right? And also the patterns of the usage also changing over time, right? Previously, maybe we have some experts using, so not experts, we have senior users. So people who have some knowledge about how to use the system, right? For example, early stage, so not everyone can use a BlackBerry phone to email, to send email, receive email, right? But nowadays, like a kid may be able to use a phone to access Facebook, access TikTok, for example, right? So we have rapid growth of users and also the varying usage patterns. So we need to make sure so our system can still handle this growing numbers, can still handle the varying usage patterns. Okay. Because of this many large number of users, the systems can suffer from this scaling issues, performance issues. For example, healthcare, the healthcare website suffers from an increasing number of users, and the results is that the people cannot load the web page anymore. Right? In fact, as we discussed before, most field problems for large-scale systems are rarely functional. Instead, they are performance or load related. In addition to the Amazon Web Service example we gave before, other examples, for example, 1 hour global outage of PayPal lost 72 million in revenue. Right? This is because of performance issue. Another example of Flickr. The Flickr outage impacted 69 million users in 2013 because of another performance issue. So we need a performance testing to identify such issues so that we don't have these issues in a production environment. We identify them before the system is deployed to users, right? How we can do it? We need to simulate a large number of users using the system at the same time, right? That is why we need performance testing, right? So what is performance testing? So other tests and methodologies to measure, verify, and validate the performance of the system. It's part of software performance engineering, right? So we use performance testing to demonstrate that the system comply with the performance criteria or performance targets. We can compare two systems or two versions of the system to find which one is better or to identify regressions, right? And we also need to identify the components that cause the system to not perform well. We need to identify the bottlenecks, right? So this is a performance testing. There are different types of performance testing. The first one, load testing. This is the most common one, right? So we test the performance of the system under the expected load, but large load, right? A number of users perform a specified number of requests during a given period of time. Others include stress testing. We test the limits of our system's capacity. We stress our system by using a lot of users to use the system. Okay, endurance testing to test so how long the system can survive under expected load for a long time. Spike testing test the reaction of the system by suddenly increasing or decreasing the load generated by a very large number of users. And capacity testing to test the system to find the maximum capacity. Configuration testing to test the different configuration combinations and verify their impact on the performance of the system. Okay, so we have this many types of tests, and today we will focus on load testing, right, which is the most common form of performance testing. Sometimes we just using these two terms, performance testing and load testing, interchangeably. Okay. So whenever you have questions, you can ask through Slack or raise your hand. Okay. So here we have a visual concept of what is performance testing, right? So first we have a load generator, right? This load generator can send a request to our systems through the network. Node generators can be actual users using the system or computer simulated loads. Okay. Oh, these requests are sent to our application under test. For example, OMRs, application under test, and then this running this test on this application under test would produce data such as logs or performance counters or performance metrics, and then we can analyze such data. Okay. So basically, performance testing mimics multiple users repeatedly performing the same tasks. It takes a very long time, a lot of resources. We have test design, test execution, and test analysis, 3 stages. Okay. Let's look at the detailed process. As we said, we have a test design, test execution, and test analysis, right? So here, in this process, after test design, we get the test cases or testing load, right? Then we execute the performance test, produce a performance test data. So we analyze the performance data, produce performance test report. Okay, this is a general process. Let's look at each step separately. Okay, first, designing performance tests. So here we will talk about 3 parts. First part is to design realistic loads. We want to mimic the realistic loads. Right? Second is the designing fault-inducing loads. We need to identify performance issues. The third part is to perform load design optimizations and reductions. Because if we want to mimic hundreds of millions of users using the system, it can consume a lot of resources and time, right? So we want to reduce those resources used and optimize our load test design. Okay. Let's look at the first one. Designing realistic nodes. So we have a large number of users. For example, for e-commerce system. So then we can analyze how actually users use it. The first way is to use something called an aggregate workload. So for this aggregate workload, we statistically count like what is the distribution of the users using different functionality or features of the system. For example, here in this example, so people perform a login action for 10% of the time. People perform browsing action for 80% of the time. Purchase or log out for the 5% of the time, respectively. So this is the aggregate workload. So we then, based on this distribution, we can mimic the realistic workload, right? The second way is using use case, right? In the use case, we mimic the user's usage sequence. For example, people first do login, then they browse the items, then they purchase items, then they log out, right? Then when we design our test case, we mimic such a flow, such a sequence. Okay, this is the two ways to conduct the design of realistic workloads. Here, an example of characterizing an aggregate workload, right? So we have a workload mix first. We understand the distribution of the user actions across different actions, across different features. For example, browsing account for 30% of the user actions, right? So then also we need to determine the workload intensity, like how many users, how many requests during a small period of time. For example, like 5 requests during 1 second, right? So based on this workload intensity and workload mix, so we can design the requests. We can simulate a realistic workload. For example, here in this example, then we can, within 1 hour, there are 300 requests, right? Then 30% of them are for browsing. So we can have 90 browsing actions in our workload. Purchasing 10%, so we can have 30 actions for purchasing, and the rest of them for searching, right? So this is how we use the aggregate workload to design our test load, okay? Yeah, the test load may change over time. You may consider a steady workload. You may repeat the same workload for an extended period of time, right? This is steady workload. Or you can have a stepwise load. You can gradually increase your workload, right? So they are used for different purposes. For example, if you want to identify memory leaks, so you want to use a steady workload. And when you are using a steady workload and you find your memory usage increase gradually, then there probably is a memory leak, okay? Another way to have a aggregate workload is to get the data from the users or from the interviews with domain experts or the competitors' data, right? Especially when you don't have a history of data, you can have these ways to get the data, right? This is how you get the distribution of the workloads, either from your own data or from users or from domain experts or like from competitors' data. Okay. Another way of designing workload is using these use cases, right? So the first form is UML diagrams. So you have a UML diagram, and in this diagram, you model how users actually use the system, right? For example, the first to log in, then they may do download or navigate or delete or upload, right? Then they log out. So these are the possible actions of the user, and you design your workflow based on this diagram. Okay. Another one, so maybe more common, is the Markov chain. So here, so what does it mean, right? So the users first do logging, and then they may do search or browse. For 40% of the cases, they do search, and for 60% of the cases, they do browsing, right? And after search, they may do purchase or browse. For 95% of the cases, they do browsing, and only for 5% of the cases, they do purchasing, right? So when we design our workloads, we need to randomly assign these actions based on these probabilities, okay? How we derive such, for example, how we derive those this Markov chain, right? So we can look at our historic data. For example, we look at our logs, right? For example, we look at our web access logs for the past few months. Within these logs, we could understand actually how users use it and what's the probability of having one action after another, right? Let's look at a smaller example. So in this example, we have only 3 log lines, right? And if you look at the details, we see for there are fields like a customer ID or action, right? For example, DS browse, the action, purchase is an action. User ID, we have a 41 and 5961. Another user ID is a 41 or customer ID, right? So here we identify a action sequence here. For the customer ID 41, it first do browse, then do purchase. So we have this browse to purchase relationship, right? If we have a lot of logs, then we know, okay, after browsing, users has a certain possibility to do purchase and another possibility to do a lockout, for example, right? So we can determine a Markov chain like this one. Do we have any questions here? So we will do, okay. So we will do an exercise for this later, okay? There's one question here. How to represent the notion of a successful or failure logging, right? So solution, think about it. The solution is from logging to logging itself, we have an arrow, right? That's how to represent the notion of successful or failure logging. We talk about how to design regular workloads, realistic workloads, right? To perform a load testing. Another one, sometimes we want to design workloads to identify performance bugs, right? So we need to design fault-inducing loads. How to design fault-inducing loads? We have 2 ways usually. The first way is to look at the source code. Second way is actually use a system model. Let's look at the first way first. From source code, we do source code analysis, for example. We do data flow analysis. Then we can identify the potential load sensitive modules, right? So we identify one module that is very sensitive to a large number of loads, a large number of users using the system, or to sensitive to a large load. So we can purposely test such a module. So this is how we, based on source code analysis, to design our fault-inducing workload. So here, there's some formal way, there's a load sensitivity index that indicates the net increase or decrease of a heap size used for each iteration. So if we find that one iteration can significantly increase the heap size, we may test it to find the performance issues related to the heap heap usage. Okay. Yeah. So you can refer to a paper to check the details of this method. Another way is called symbolic execution. This is another way of source code analysis for designing fault-inducing load cases, right? For example, here, so we can, based on this execution, so we can we can infer response time. We can infer like which path would lead to a long response time, right? So we can purposely test that long response time path. Okay. You don't need to understand details, but you may check the paper to get the details. Okay. Another way is to use the system models, right? Use a system model, for example, using genetic algorithms to find the fault-inducing load cases. First, we have our regular cases, right? So here, for example, these are the sequences, the 4 steps of user actions in a regular workload, right? Then we can do a random mutation. We change one workload, one action to another. We just do a random mutation. We don't find this in our historical data, but we want to do a mutation to actually introduce some fault-inducing workload case. We can also do something called crossover from 2 workloads. We switch part of them to form new workloads. Those workloads are not exist in our historic data, but we can create them to identify the performance use, because users may use such Python in the future, even though they don't have this such case in the past, right? Yeah, this is just an example of how to use system models to conduct this to create the fault-inducing load cases. Okay. Yeah. Another way is to another part of load case creation is to reduce the load cases, or to optimize the load design, right? For example, can we reduce the load testing effort and cost when there's limited time and hardware software resources? Can we do it? One simple way might be do an extrapolation. For example, if we have a stepwise load testing in which we gradually increase the workload, right? Then we can only examine a few load levels. We examine 1 user, 5 users, 10 users. Then we extrapolate the system performance for the other load levels. For example, from 1, 5, 10, we can extrapolate the load level of 3 users, 80 users, for example, right? Okay. Another way is to use a probability to cover as many cases as possible, but running a smaller number of test cases. Okay, let's look at an example. For example, for a telecom system, so there are different usage patterns. In this example, this is one usage pattern, right? So during a period of time, there are 2 active calls, 3 leaving voicemail, 0 updating profile, 1 checking status, 5 active voice mail. These are the action patterns within, for example, within 5 minutes, right? And that for another state is 0, 0, 0, all zeros. This idle state of people do nothing within 5 minutes, right? So we identify all these states. For each state, we identify the numbers, right? Then we sort them based on the numbers, right? Then we can calculate the accumulated probability of these states. For example, here, in total, there are 857 cases, but using only 206 cases, we can cover 80% of the cases. So if we want to reduce the load cases, we just run the 206 states, but still cover 80% of the cases, right? This is two ways about how we can reduce the load cases. However, we cannot just look at one historic data and the rest forever, because realistic load tests are based on field workloads, but field workloads change over time. In 2012, you have this number of users. In 2013, you have another number of users. So we need to continuously update our load cases. Okay. We talk about how to design performance tests. The most important thing you want to remember is we want to simulate a realistic workload. We can check historic data, we can check data from our competitors, or ask domain experts, right? And we also need to identify the load cases that may introduce failures or performance issues. And also we have ways to reduce the load cases, right? The second one is executing performance tests. This is the second step. So we will talk about how to produce the loads, or how to drive the system under test, right? Of two ways, we have three ways, but here we'll focus two ways: live user-based execution, driver-based execution. This is the two ways we use to send the request to a system or to drive the system. And we'll talk about how to set up or how to configure the performance testing environment, and how to actually generate a load and terminate the performance test, and how to monitor test and connect data. Okay, talk about it one by one. First, live user-based text execution, right? How can we evaluate like a large number of users using the system at the same time? The simplest way is to actually invite a large number of users using your system and test it, right? Those are actual users actually using your system, so you can test the performance of your system. The users may be selected based on different testing criteria, like locations and their browser types, and their, for example, their purchasing patterns, right? Benefits. It reflects realistic user behavior because they are realistic users, they're actual users. And also you can obtain real user feedbacks on acceptable performance and functional correctness. You can ask them about their opinions of your system, about the system. Okay. Drawbacks. It's hard to scale. For example, Facebook can handle like hundreds, thousands of millions of users at the same time, right? How can they invite so many users to test their system? It's hard to scale, right? And also, because we need to instruct users to do certain things, the testing complexity is limited. We cannot ask them to do very complicated things, otherwise they will be lost. So this is a live user-based test execution, right? Actually there's a website or a platform called U-Test. In this U-Test, you can register and become something called U-Tester. As a U-Tester, basically you are a freelancer. So people, those companies, they will recruit testers to test their systems. So you act as one user in this live user-based text execution, and you get certain payment. That is a I found this on the web. That is a platform for U-Test. Okay. Yeah, so you can check the website of U-Test to know more about the live user-based text execution. The second one is a driver-based text execution. We don't invite actual users. We use a computer to simulate the user behaviors, right? The computer will send a request to the system under test. Because why we can do such a simulation? Because when users use their system, actually send requests to the system, for example, to Google search engine, right? They send the request to the engine. We can automate the sending process of the request, right? We can just simulate the process of sending requests to a system using a computer, right? As the driver-based text execution. So there are specialized tools to run the tests, to generate the load, right? Such as load chain, load runner, web load, JMeter, peer unit. So one thing, the JMeter is very common. It's a very popular tool used in modern software companies. So here, we'll also in the assignment and exercises, we will use JMeter to generate the load to the system under test. Okay. Benefits of this way. Okay, easy to automate, right? It's a scale for a large number of requests. We don't need a large number of users. We just need computers, so it's easier to scale. Drawbacks. We need to configure our load driver. Maybe it's hard to track some system behavior, for example, audio quality or image display. When people look at it, actually, it's maybe easier to capture the quality, but when you are using something to automate the process, it's hard to understand the quality, right? This is driver-based test execution. So there are three things to consider when executing a load test. Basically, there are test setup, node generation and termination, and test monitoring and data connection. Right? We will look at them one by one. First, test setup. How we do? First, we need to determine whether in which environment we want to run our test, right? For example, we may want to test our system in the field using actual users, right? That may be very costly. And we will to determine which hardware we want to use to do the test, right? You either using your own hardware or using cloud-based support, right? And we need to create a realistic database, create realistic load, right? So maybe we can have historic data, and maybe we want to sanitize the field database because we want to remove this private information, right? We need to remove username, user ID, for example. And we will need to mimic those realistic network traffic. The network traffic is not ideal usually. Sometimes you have delays, right? And you have random delays. You need to mimic such situation. And we shouldn't deploy drivers on the same machines with a system under test. We need to send the test over the network to the system under test. But in our assignment, you can use this. You can use them on the same version because you may have only one version, right? It's okay. Yeah. We have a live user-based execution, right? Talk about. In this live user-based execution, we need to recruit our testers. We do training them, right? We need to give them instructions. For Java-based execution, we need to develop the programming to automate the generation of the driver of the load. Okay. We configure the drivers as well. Second aspect is load generation and termination. So how to generate when to how to determine when to generate load and when to terminate the load, right? There's the static configuration. You configure everything before you run the test. For example, you configure in the first hour, I will have 500 users to use the system at the same time. And these 500 users will log in to the system and perform some actions such as reading the emails, writing the emails, and something like others, then log out, for example, right? There's a static configuration. A dynamic configuration, you may change your load cases based on the feedback from the environment. For example, you find that the performance is very bad, then you may want to reduce the number of users using the system. That's feedback-based one. Right? For live user-based, you only can only do static configuration because you need to tell people what to do exactly before they do it, right? That's normally like only using static configuration. But for driver-based, you may use both static and dynamic. You can use you can write some code, for example, to check the feedback and then to adjust your load cases. Okay. So another aspect is to monitor the data during the performance testing. There are different tools. The easiest one, like in Windows, we have a task manager. We can check CPU usage, your memory usage, those things, network usage, right? So these are the basic form of system monitoring, right? And in Linux system, you have a pit stat, right? So actually, you can check the status of a process, of each process. Another tools like JConsole, CAVD, and AppDynamics. In these tools, you can monitor the performance of your system during the performance test. Okay. These tools basically can be classified into two types. The first type is agentless monitoring. What is agentless monitoring? So when we are monitoring a system, we don't put an agent to the system. We check the performance of our system based on the data provided by the platform, by the operating system. For example, provided by Windows, right? We just check the result. We look at the task manager, like JConsole, right? The same thing. Another type is agent-based monitoring. When we monitor a system, we add one small tool, one agent, and let it monitor the system under test during this performance testing, right? So this small agent would record the performance of the system under test and send it back to our load test engine or load test analysis tool. Examples like AppDynamics and CAVD. Okay. So we talk about the second step, executing performance test. The last step is analyzing performance data. The last step is analyze performance data. So we analyze our performance data based on our targets, right? Performance testing targets. The first one is verifying against threshold values, right? For example, the speed of our system for conducting a search request should be less than 3 milliseconds, right? That's a threshold. And also we want to detect problems, failures, performance bugs, right? And that's why we want to build performance models. Such models can help us understand the performance of the system, identify bottlenecks, or to identify improvement opportunities, identify performance regressions as well. So analyze performance data. So what is the data, right? So we record certain things like performance metrics, or we call performance counters. So here we show the example of some performance counters. So these are time series data. So we have, for each row, we can see there's a timestamp, right? So this at what time and the other columns are the performance counters, like disk rate, so how many reads per second, how many write per second, how many per page file per second, the memory usage, CPU usage, response time, throughput, or the metrics. You record these counters like in a time miner based on each time step. Okay. Other data, for example, execution logs, right? So also at each time, you have a message. This message indicate what happened in the system, the execution logs. So those are the data you can analyze, right? So to verify your performance test goals. So for example, to verify against the threshold values, you can determine a threshold from the requirements, from your non-function requirements, right? You can compare the test results with the threshold specified in your non-function requirements. Also, the threshold can be from a prior version. For example, you need to make sure your version 2 is not slower than your version 1. The version 2 is not using more resources than version 1. You don't have performance regressions, right? So verifying against the threshold values. Second, to determine known problems using patterns. There are some patterns of errors. For example, when there are memory leaks, the data may show some patterns. These patterns are known already, right? And also there are some patterns in the logs. For example, you do an error keyword search, you may find those errors in the execution logs to find the problems. Let's look at an example of how we can identify those known problems using patterns. And here you in this example, so basically it shows the CPU and memory usage of the system, and the horizontal axis shows the time, right? The vertical axis shows CPU and memory respectively. So we can see that the CPU is not steady, right? Sometimes we see a very low usage of CPU, right? What happens? So this is a known pattern that it shows that there is a deadlock. So this deadlock causes everything to wait for some resource, right? So there's no CPU usage at this time. This is one pattern. For memory, you can see under steady workload, but we see a gradual increase of memory usage, right? So this probably indicates a memory leak, right? If you fix this memory leak and CPU and deadlock problems, we probably will see steady memory usage and a steady CPU usage, right? That's how we use known patterns to identify problems, right? Also, we can check execution logs, right? We can search errors in the logs, right? Or better, we can use a tool to visualize the trend of the searched keywords, right? For example, we search errors, and we show this bar shows the number of errors across time, right? You can see the number of errors reduce, or we can show the number of successful actions, right? For example, we show some like a user successfully logging in, right? We can see how many number of users successfully logging into the system over time. We see the number is reducing, for example. Another way to analyze the performance data is to build performance models. There are two types of performance models: machine learning model, a queuing model. We will discuss these two types of our performance models in the next week. Okay, so these models, using this model, so we can understand the problems such as what if, right? What if I increase the number of users by 20% in the next week? What will happen? Can we predict how many? So can we predict the CPU usage, memory usage? Can we predict whether we need more resources? Right? And the capacity planning. Do we need to plan? Do I increase the capacity? Right? Anomaly. Is there any problem in the system related to performance? Right. So these performance models are actually very useful in practice. Okay, we'll talk about performance models in the next week. Okay, this is about performance testing, and I think we need a break. So this time we have a slightly longer break. We will come back at 2:25. Okay, we come back at 2:25, 10 minutes or almost. Do you have any questions here? Okay.